Welcome to ETAP webinar of STAR ZSI scheme for PD evaluation and arc flash mitigation. I'm your presenter, Kun Ran. In today's webinar, we're going to discuss about ZSI fundamentals, what is ZSI, ZSI applications, and ZSI wiring and interlocking. Also, we'll use ETAP STAR mode to verify the ZSI operation for different fault types. We'll see how ZSI works in the auto evaluation. Also, we'll show you one demo how ZSI scheme can help for arc flash hazard mitigation. What is ZSI? ZSI stands for Zone Selective Interlock. It's a protection scheme used with circuit breakers to improve the level of protection in a power distribution system. The purpose of ZSI is to speed up tripping for some faults without sacrificing the coordination of the system. And how does ZSI work? The upstream and downstream breakers are wired, and the downstream breakers send a restraint signal for detected fault. The upstream breakers start restraint timer for tripping, and the downstream breaker trips on the unrestrained time if it's not self-restrained. Let's take a look at the right side capture, and I'll show you how this different step works using this example right here. In this capture, we have 4 breakers. The green ones, blue one, and the yellow one. The green ones are the feeder breakers, right, which does not have any input from downstream breakers. There are no downstream breakers, so there's no input for this green breakers. And the blue one is the upstream breaker of these 2 green breakers. And the input of this blue breaker is from the output of the green breakers, the feeder breakers. And the upstream yellow breaker right here, it received a signal from the blue breaker. So as you can see, the output are connected to the input of the yellow breaker right here. And there's no upstream breaker, so this output does not connect to any other breakers. So that's the basic wiring. So we make sure upstream and downstream breakers are wired. Okay, so next, when there's a fault happen at point A, right, if this breaker detects a fault, it will issue a restraint signal, and this restraint signal is sent to the connected breaker, which is the upstream blue one. So in this case, once the blue breaker receives this restraint signal, it will start a restraint timer for tripping. So it's adding an additional delay on top of its trip. And at the same time, downstream breaker trips on unrestrained time if it's not self-restrained. So which means if this breaker does not have a self-restraint wiring, which means the output is connected to its input. If it's not self-restrained, it will just use unrestrained time, which is the faster tripping time for tripping. Let's take a look at restrained and unrestrained settings. In this star view plotted on the right, we have 2 curves, the green curve and the blue curve. The green curve is plotted using the restraint settings. There's a delayed band right here, which is slower than the blue one, and it's leading to longer time to trip. That's why we call it restrained. If there's a pickup available for the restraint setting, typically it will be larger, and that will be depends on the manufacturer and the model. The unrestrained curve right here are plotted with unrestrained settings. the delay band is faster, so it's leading to a shorter time to trip. Let's take a closer look at the ZSI wiring schemes. Each manufacturer has its own ZSI wiring scheme. ZSI terminals are breaker specific, which means you can see different wiring schemes based on the different breakers. And ZSI terminals can have phase terminal, ground terminal, or phase and ground terminals at the same time. Sometimes for phase terminal, it includes short time only, and sometimes it includes both short time and instantaneous. If there's a jumper connected between the ZSI output and input, which will lead to the self-restraint. Right? On the right side, as you can see, this is a extract from square DLE breaker wiring schemes. Right? We have the short time restraint in, short time restraint out terminals. We have the ground restraint in and out terminals, and also we have a restraint common terminals. The common terminals are connected together, and here the restraint out terminal for short time and ground are connected to the restraint in terminal of the upstream for the short time and ground. Right? That's how the upstream breaker can receive the restraint signals. If we have a jumper installed for a self-restraint, and that will connect the short time restraint in and out together, and the ground is restraint in and out together. And that is the jumper for self-restraint scheme. In this slide, we have two more examples. One for Siemens WL breaker wiring scheme, one for the color hammer breaker ZSI wiring scheme. So to the left, you can see we have input 3 and 4 terminals, output 5 and 6 terminals, and see output is connected to the input of the upstream. And same here for the zone 2, and 5 and 6 are connected to the upstream 3 and 4 terminals. And you can see the delays are different, right? The zone 3 has a 150 millisecond delay, and if the zone 2 received a restraint signal, it will have a 200 millisecond delay. And for zone 1 right here, the delay time is 300 milliseconds if the restraint signal is received. On the right side, the color hammer breaker, you see we only have one input and one output and one common, right? So this is how it's connected, right? The one good thing to mention right here is you can have the ZSI wiring through different breaker models. Right here on the color hammer one, you see this is a Digitrip 1150 Plus. Here is the Optum 1050, and here is the PXR 25. So as long as you have the proper input and output connected to the upstream, and if they are the same manufacturer, they will give you specific instruction on how this breaker can be wired using ZSI. So we talked about the wirings, different wiring schemes for different manufacturer. Now let's take a look at the ZSI settings. So most manufacturers do not have ZSI adjustable settings, right? They will have the fixed pickup and fixed delay band. And also ZSI is available for short time and ground for most cases. And for some manufacturer like GE, right, they have ZSI adjustable settings. And also they include the threshold ZSI. And as you can see at this capture below, right, the left one is GE. It's very powerful that you can turn the ZSI restraint settings for short time, instantaneous, and ground. And you have the adjustable capabilities for short time delay and slope, for ground delay and slope, and also you can enable the threshold, right, for ZSI short time and instantaneous. And on the right side, we have the Siemens. Siemens says you can have the ground, short time input and short time output, or short time and ground, but you don't really have any settings adjustable. So what you can choose is just using the ground ZSI, short time ZSI, or both. Let's take a look at ETAP program and how we can turn ZSI settings on, how we can implement ZSI wiring schemes, and how we can utilize the implemented ZSI schemes for protection coordination studies as well as arc flash studies. In this project, we have two revisions available, base and ZSI. In ZSI revision, we have the ZSI settings enabled and the wiring schemes implemented, so it is ready for demonstration for protection coordination studies. But before we go to the ZSI revision, let's go ahead and take a look in base how we can enable the ZSI setting for this specific LVCB-main1 breaker. So first, let's highlight this model and create a star view for this breaker. So in the star view, as you can see, we have a low voltage solid state trip for this Digitrip 310 plus trip unit. And we can double click to open the breaker editor, and we'll go to the trip device page of this breaker. In the trip device page, we can find out we have a long time function and short time function, and also we have the instantaneous override available. And we have the ground curve available for this trip unit as well. We have the zone selective interlock checkbox available under the trip device section. If we turn this option or this checkbox on, we will see the ZSI type is displaying and showing we have the short time ZSI band setting and we have the ground band setting available. If we click all this drop down, and we will find out all the settings are fixed, right? And we cannot change any settings. So this ZSI setting is unrestrained based on this label we displayed right here. And if we click OK, we will see the unrestrained curve is plotted on the star view for phase. And if we switch to ground, we will see the unrestrained curve is displayed as well. Right, for unrestrained settings, as we discussed earlier, we are expecting this unrestrained curve to pick up when the fault is on the bus, right? When we have a fault on the bus main 1, we are expecting this breaker to trip faster, which is using the unrestrained curve. And when the fault is at any of the feeder terminals, this breaker should receive a restraint signal from the downstream breaker. So in that case, we want this breaker to trip slower, right, or have an intentional delay, and so it will use the restraint setting for tripping purpose. Okay, so let's go back to the phase mode and double click to open the breaker editor again, and let's switch to ZSI page, and you notice we have the library ZSI radio button selected. So for this Digitrip 310 Plus model, we have the library ZSI settings model. So you have the ZSI setting. If you're using a model which does not have the library ZSI and you turn the ZSI on, you see the user-defined ZSI is selected. So based on the function available in phase and ground page, you see different functions available for ZSI. So this one, we only have short time and ground available for phase and ground. So you see the short time ZSI and short time ground, they are available. And if you're using user-defined ZSI, you can define the pickup for the ZSI setting and the band for ZSI setting. And you can also define what is the type of the curve of the ZSI. It could be restrained or it could be unrestrained. You can just select based on these two radio buttons. Okay, and let me switch back to library ZSI and press OK. And now we know we can plot the ZSI settings by enable the checkbox. We can see what is restrained or what is unrestrained curves and what will be used for the studies. But we still have to plug in the information for the ZSI wiring. So we can double click to open the editor again and go to the ZSI wiring page. In ZSI wiring page, we have three different tables. We have the input, output, and interlock from downstream breakers. So for the input, we can select one input using phase and ground terminal at the same time, or we can have a separate phase and ground terminals for input. And same as the output, we can have phase/ground for output, or we can have two separate phase and ground output terminals. So for this case, we'll just use the phase and ground terminal together. And for the input of this breaker, we have the interlock table available that we can define what to be selected. And by default, the self-restraint is checked. And if you want to model or edit this downstream interlock breakers, you can uncheck this checkbox and define what needs to be interlocked with this LVCB-main1. So I have this predefined. Now let me just delete everything, right? You can use add, insert, or delete button by modifying this table. And we have this IBAT zone button available. So you can just simply press this button and ETAP will automatically detect the downstream breakers that you can use for interlocking or implementing the schemes for ZSI. So here, once I press this add by zone button, all the feeder breakers are added right here, and you can check to select all of them and to be used as input of this breaker. Right? For each row, you can see what is the device ID, what is the manufacturer, and what is the breaker model, and what is the trip device model for that specific downstream breaker. And if the ZSI is enabled, you see ZSI checkbox is checked, and you'll find out what is the output signal, right, for the downstream output terminal. Right here is blank since we don't have any ZSI settings enabled, but I'll show you an example in the ZSI revision so we can run the simulation for that. And based on the project or the system you have, right? So here we only have 3 feeders available, and if you have more system underneath, or you're selecting a breaker right here like this LVCB1, and you want to interlock with multiple levels or zone levels away, and you can define how many levels you want to add for your input by changing this number of zone level away and click add by zone. Okay, let me press OK, and now let's go to the ZSI revision, and then I can show you how ZSI was implemented in this revision, and then we'll go ahead and run a sequence of operation to show you how ZSI is stripping. So in this revision, you can see a lot of elements. They are highlighted in green, which means they have a different settings compared to base. And let's just quickly go through this LVCB-F1, F2, and F3 and see what we have. If we open the LVCB-F1 and go to trip device page, so we'll find out the zone selective interlock is enabled, and this one has short time and ground ZSI, and this is basically the same trip unit, Digitrip 310 Plus, and ZSI setting is unrestrained. And let's take a look at the ZSI wiring page. Okay, so for this one, right, we are having a self-restraint checked for this breaker, which means the output signal will send to this breaker itself as well. Okay, so let's go ahead and check the LVCB-F2, similar trip unit and with the self-restraint checked, and LVCB-F3, similar, right? We'll go to the LVCB-main, and now we can see we are implementing a scheme between the LVCB-F1 and LVCB-main1, which means if there's a fault happening at the induction motor 1 terminal, and this LVCB-F1 will send a restraint signal to LVCB-main, right? So we are receiving that restraint signal from LVCB-F1. You see now the ZSI is enabled for this LVCB-1, and the output restraint signal is phase and ground. So we're reading this phase and ground restraint signal from this input, and then we'll decide what to be used, right? We use restrained or unrestrained, right, accordingly. And also we can check the LVCB1, right? So we haven't implemented any zone selective interlock between the LVCB-main1 and LVCB1. So now let's press OK, and then we can do a simulation for two different fault locations. We can fault at this terminal, and we can fault on this bus main 1. So before we place a sequence of operation, we have to go to the study case and check if we have the ZSI considered enabled for sequence of operation. I open the study case right here, and we can switch to the sequence of operation page. So right here we can define what is the fault value, what is the fault type, and how many protective devices to be considered for the sequence of operation study, and if we want to consider the zone selective interlock, right? So, and the consider checkbox is checked, and we have a 3-phase fault type selected. So now we can simulate a 3-phase fault for our ZSI revision. Let me press OK. Let's insert a 3-phase fault at induction motor 1 terminal. And ETAP will run the simulation and display the sequence viewer automatically. And we can see the first event is highlighted, and we are flashing with that specific events. Right, we have the sequence op slider available in ETAP 22, so you can move the slider to check each event. Right, so here I click the next event, so you see the LVCB main 1 is tripping second, right, and at 300 milliseconds. And my first event LVCB-F1 is tripping at 49.3 millisecond, right? We have the proper coordination between the LVCB-F1 and LVCB-main1. But let's take a look at each individual star view first, and then create a star view between these two breakers and check the coordination. So when the fault is happening on this motor terminal induction motor 1, and the LVCB-F1 is tripping first, and we can create a star view for this LVCB-F1. We can double check right here, the restraint curve is tripping and the trip time is 49.3 millisecond. And we can double click on the curve to open the breaker editor. And in the wiring page, since we have the self-restraint checkbox checked, so when the breaker detects a fault, it will send a restraint signal to itself, and it will trip based on the restraint setting, which is perfectly correct. If we are going back to trip device page, we can double check the ZSI setting is unrestrained, the phase setting will be restrained, so we are using the phase restraint curve for tripping. That is what we expected. And also, if we click on the second event, right, the slider will update with the time, the tripping time available, that is 300 milliseconds. We can create a star view for this LVCB-main1. And as you can see in the normalized star view, the tripping time is 300 milliseconds, which is using the restraint, which is the phase curve, right? This breaker is receiving the restraint signal from the LVCB-F1, so it will use the restraint curve instead of the unrestrained curve, right? That is also what we expected to have. And now let's go back to our one-line diagram and highlight both LVCB-F1 and LVCB-main1 and create a star view. Now we can see we do have a proper coordination between the low downstream LVCB-F1 and the upstream LVCB-main1 because of the ZSI scheme, right? So this is sending a restraint signal to the upstream, so the upstream is using the restraint curve. Now let's change the fault location from the motor terminal to bus main 1. I'm moving or dragging this fault insertion and put it on the bus main 1. And from the sequence viewer, we can tell the LVCB main 1 is tripping first, and it is using the ZSI phase on restraint curve, and trip time is 62 milliseconds. We can go ahead and create a new star view for this breaker, and we'll find out it is tripping using the unrestrained curve right here, right? This is what we want to achieve with the ZSI scheme. When the fault is on the bus or at this breaker terminal, we want this LVCB-main1 to trip faster using the unrestrained curve. If the fault is at the feeder terminal, we want this breaker to have a delay that we can achieve the coordination between the downstream and upstream breaker. Okay, and let's go ahead and remove the fault, and we can switch the steady case to line to ground, and we can simulate a line to ground fault at the motor terminal and see what will happen. And let's place this line to ground at this induction motor 1 terminal. And we can see the LVCB-F1 is tripping first the phase restraint curve is tripping, the ground restraint curve is tripping, and the LVCB-main 1 is tripping for both phase and ground restraint curves. So this time we'll just plot both breakers in the same SOAR view. You highlight both breakers and click to create a new SOAR view. And for phase fault, we can see, right, the downstream breaker is tripping with restraint because we have the self-restraint checkbox checked in the wiring page. And the upstream is tripping as restraint because it's receiving the restraint signal from the downstream breaker. And let's switch to ground, right? So we can see the ground, the downstream and upstream, they're tripping at the same time, right? So in this case, what we can do, right, we can go ahead and open the upstream breaker and increase the delay band, right, to 300 milliseconds. Press OK. So in this case, we can have proper coordination. So this is what we want to achieve. And now let's go ahead and place the fault on the bus main 1, the line to ground fault. And here you can see my LVCB main 1 is tripping for phase and ground curve. We can create a SOAR view for the LVCB-main 1, and to make sure we are using the faster unrestrained curve for tripping. So this is my phase and this is my ground. Remember, I changed the ground trip time to 300 milliseconds, but for unrestrained we want faster tripping, which is 62 milliseconds right here. Okay, so you can see the 62 millisecond is used as unrestrained. Alright, so that is the demonstration for how sequence op works with ZSI schemes. So as we discussed, we want to achieve coordination when fault is at downstream, and we want to achieve fast tripping when the fault is on the bus, right? And let me just close this SOAR views and sequence viewer, and we can run a simulation using the SOAR auto evaluation. For auto evaluation, we have to open the study case and go to SOAR auto page and verify the correct evaluation and fault are selected. Also for ZSI simulation, we want to have the consider ZSI option checked. So in this study case, we have both protection and coordination evaluation selected, and the fault type is for phase and ground. We click OK, and we select the bus main 1 and run auto evaluation. So auto evaluation is automatically run for the bus, and you can see for this bus we have a green, which means it's passed. We go to the bus page and click expand, so we can find out, right, the bus protection is good and is using the unrestrained curve, right, for the main, right, because we are assuming the fault is on the bus, so the unrestrained curve is used for protection. And if we go to the coordination page, and let me maximize it, and you see ETAP is simulating the upstream breaker and downstream breakers for ZSI restraint and unrestrained signals. So let's first take a look at here, right, between the main LVCB LVCB-main1 and LVCB-F1 for line to ground fault, we can find out we have proper coordination right here. And the downstream PD, we are using the phase restraint and ground restraint because it is self-restrained. The upstream breaker, LVCB-main1, ground and phase, they're using the restraint curve because they are receiving a restraint signal from the downstream breaker. For three-phase fault, right, we can tell they are properly coordinated up to this amp range. So we have a slight overlap between this instantaneous override section with the instantaneous override section on the downstream, right? So except that, we are fine, right? From this beginning of the short time band up to the maximum fault current, we have clear gap for coordination. And similar, right, for the other pairs, we can check, right, without ZSI interlocking, we don't have proper coordination between the downstream and upstream. You see they're not coordinated. For three-phase, you can also see, right, they are not coordinated because we don't have the ZSI scheme wiring implemented for LVCB-F3 and LVCB-F2. Right, so you see a similar case for LVCB-F2 line to ground and LVCB-F2 phase fault, right? So no coordination at all. So that is the benefit of setting up a ZSI wiring scheme, enable the ZSI settings, and that we can achieve the coordination when the fault is at the downstream breaker. And that is how you can simulate the ZSI scheme in the auto evaluation. And in the protection pages, right, ETAP will use the correspondence curve for tripping, and for coordination based on the fault location, ETAP will plot using the correct restraint or unrestrained curve for coordination study. And now at the end, I just want to show you how you can get benefit from the arc flash study based on the simulation we run for sequence of operation. The purpose for ZSI is to achieve coordination and arc flash at the same time. So we want faster tripping when the fault is on the bus, right? So we want to get a faster fault clearing time if there's an arcing fault. But for protection and coordination study, we want to have proper coordination between the downstream and upstream. So let's go ahead and simulate in arc flash mode. In arc flash mode, we have the consider ZSI option in the study case as well. And here I have two study cases, one for not consider ZSI, the other one is arc flash with ZSI. And let me open the study case and go to the clearing time page. So you find out for this arc flash with ZSI study case, I have the consider ZSI checked. And for arc flash study case, I don't have the consider ZSI checked. So let's simulate an arcing fault on this bus main 1 and to see how ZSI makes a big difference for arc flash study. And now let's use the arc flash study case, which is without ZSI. We can insert a fault on this bus main 1 and we press OK. So you see what is the tripping time for this bus main 1. The fault clearing time for this bus main 1 is 0.3 seconds. Right? It's giving you the incident energy of 8.927 calorie per centimeter square at 18-inch working distance. right? And the incident energy level is level D, right? So yeah, this is not very good result, right? And now let's take a look if we use the arc flash study case, consider the ZSI, which means we should use the unrestrained curve for faster tripping, and we can simulate the arcing fault on this bus. Click OK, and now you can see the huge difference, right? The fault clearing time is much faster, which is 62 milliseconds, and it reduced the incident energy into 1.845 calorie per centimeter square, and the arc flash energy level is level A. So based on ZSI scheme, right, it can help our system to achieve the faster tripping time when there's arc flash happening, and without losing the coordination capability in protection and coordination studies. Let's summarize today's webinar. We learned the ZSI fundamentals. I showed you how you can enable ZSI settings and implementing ZSI wiring schemes in LVCB editor. And we discussed about the ZSI scheme works in sequence of operation based on three-phase fault and line-to-ground fault. And also we discussed how ZSI works in star auto evaluation and how ZSI can help you for arc flash studies. And that is all for today's session, and thank you so much for your patience and attention. I'll see you in the next available webinar. Thank you so much.